Oh, good. Hello everyone. So this is the third one, and of the work related with the bio beginners tutorials about the in silico designing. So I just describe a brief information. What are the things important related with the in silico designing. So here is the Ramachandra part. As I already informed this in the first or second one, but Ramachandra part, what exactly I have to say? As I told you, suppose these are peptide bonds, so one amino acid interact with another amino acid. So if one amino acid, suppose if it's the plane, if you consider this is the one plane and this is the second plane, rest only you just say ignore side chains. Suppose all residue are in the single plane and side chain of this group, and all residue on single plane and side chain of this group, as shown in this figure. So all the interactions just based on the side chain. When all the interaction are involved, are the are not have to say interaction, but all the interaction are responsible how much it bend just because of side, because suppose it's a glycine hydrogen and it's a glycine hydrogen, so only hydrogen electron cloud make interference between the side chain, interfere between these angles. If this angle will be high or low on the basis of this is the side chain. If the tryptophan, so there is a high amount of electron cloud. So suppose this is tryptophan and this is tryptophan, so both electron cloud is too much. So the angle between them is decided by the side chain electron cloud. That's the concept of the Ramachandran plot. Ultimately, what is the big if this C and C interaction? What are the orientation between C and C is psi, and C and N is phi. These are the orientation. How suppose how it move like this one, or how it move like this one. So these all based upon what are the electron clouds of the side chain. Suppose if is a electron cloud of a small one, a glycine, so definitely they have a different a particular angle. If is a tryptophan, so different angle. If tryptophan glycine, so different angle. If serine, so these all calculated, and they already told that if these are in the region, so these have a this angle. So they already decided. On the basis they have to prepare a chart. So because maximum it was a minus 180 to plus 180, so they know if these two amino acids, so what are the angle between them, if these, so every 20th amino acid they know what are the angle between C and C and what are the C and N. So they know everyone, they calculate and they make a plot. So that's a Ramachandran plot. So you keep this in mind because that's a very important to get information that the protein is stable or not. Because if suppose protein is a looks like a, you have to prepare some protein or some folded or misfolded protein, you just have to check what is the Ramachandran plot of this protein, and ultimately you have find that okay, this amino acid is should be in the particular in this region. Suppose minus 62 plus 60 should be in the region of the alpha helix. But if this in the shown, if this orientation is shown in the beta region, okay, so that protein is not in that orientation as expected. So this protein is either misfolded or unfolded, such type of things. So that's a very important plot, and I think you better to understand what exactly say. Okay, I'm just going to next one. Ultimately here they told that what is the propensity means possibility. Suppose if alpha helix, so glutamic and methionine have a high probability to be in the alpha helix, same like a beta. The beta have a suppose isoleucine valine, they have a high possibility and to be in the beta seat, suppose beta turn. So these are the things. Is a propensity means possibility to be. Okay, there are some examples about helix. And so helical region is that you have to just know that suppose these are the amino acid 1, amino acid 2, amino acid 3, amino acid, just as I told in the Ramachandran part. But if suppose one amino acid interact with fourth amino acid by hydrogen bond, so one amino acid, suppose if this is a line, and one amino acid interact with the fourth amino acid, second with fifth, third with sixth, fourth with eight. If such type of interaction, because they have interaction, if you have this type of interaction, and now you just like a vertical, so one with four, so it look like helical structure. So that's a helix, and that's a helix found in the globe. That is a global protein. Not have to say, but this they not have to say, just go through the global protein. But okay, so axis diffraction by the found it would usually have found in keratin protein, it found in nails and hairs, not include cat, but everyone we can also have the same protein. So ultimately these proteins are keratin protein, that's an example, and it has been shown by the X-ray diffraction, and ultimately it had seen that the protein is a helical in nature. So as I told you, as I inform you, what are the helical protein? Helical protein, they have to just create alpha helical region. Every fourth amino acid they have to interact with hydrogen bond. Now this is suppose is beta seed. So beta seed is same thing, but they also have a hydrogen bond, because alpha helix and beta seed they have a hydrogen bond. But here they have to just like a seed like structure. Seed like structure, suppose 1, 2, 3, 4, 5, 6, 10 amino acid are here, and suppose 11, 12, 13, 14, 15, 16, 17, 18, 20 here. So suppose 10 are here and 10 are here. If now this first one interact with 10th one, second one with 9th one, third one with 8th one, such type of interaction, they're far away, not in the every fourth or in every say every fourth amino acid as shown in the helical region, they are far away. So if they are look like in this fashion, though, so they look like, suppose if these are the, so this like a seat like structure, because these amino acids interact with each other by peptide bond, and they have to make hydrogen bond with another peptide bond seat like region. If these are parallel, so these are parallel alpha beta seed. If these are antipolar, so these are antipolar beta seed. But they have to interaction with a far away amino acid, and such type of interaction is found in beta seed. So usually beta seed, what will happen? So they have a flexibility to skid. So ultimately these proteins are found in the spider web, silk, and elastic. So they have a higher resistance, and these are the beta seed structure. Now, what is the protein folding? Protein folding is my major area of interest. Ultimately, what is the thing is that you have to just keep in this mind. There's a myoglobin, because the person have got Nobel, and this is the first protein to be crystallized and all these things. But ultimately, what the protein folding? As I showed you, suppose if a thread, suppose if a normal thread, just like a thread, suppose one amino acid, two amino acid, three amino acid, four amino acid interact with each other, and interact with each other, and just like a, now if you put one amino acid from the first amino acid and put 10th amino acid, 10th amino acid, so if you just stretch as much as possible, only peptide bond is here. So that is a primary structure. That's why, so one amino acid interact with second amino acid, second with third, third with fourth, as sub 10th amino acid. And suppose n terminal of one amino acid, you just take one, and C terminal of last one. So that's the N terminal and C terminal, and there is only peptide bond among every amino acid. Okay. Now, if you use just an example, I told you, if suppose this is the thread-like structure, like white thread. If you put this thread in the water, so they definitely have to fold in some other manner. If you dip this thread in lipid and put in the water, so they different fold in a different manner. So ultimately, they decided what are the outer structure. If the outer structure are hydrophilic, so they are folded in protein in different manner. And if the outer structure of is the hydrophobic, so they fold it in different manner. So the decided that what are the structure, what are the outer surface of the protein is hydrophilic, hydrophobic, polar, non-polar, all these things, aliphatic, aromatic, all these charged, subcharged amino acid, and ultimately they have to interaction with the surrounding. If the surrounding is the hydrophilic, they have to interaction in that fashion. If surrounding is a hydrophilic phobic, so they have to interact with that fashion. So usually what happen, they have to prepare DNA to RNA, RNA to protein. So ultimately DNA to RNA, RNA to protein. So I am just going to translation where the RNA to protein, and ultimately as protein is formed, so protein, because mRNA ribosome, as I think you everyone have to aware. So ultimately, what is the one amino acid, one protein, one amino acid comes in the cytosol, then second, then third, then fourth, and they have to interact with peptide bond, because as the process of translation. So ultimately, one amino acid come into cytosol, then second, then third, then fourth, then fifth, then sixth, such type of things, which already have to interact with the previous one by peptide bond. But as it come in the cytosol, so cytosol environment is a what is the buffer of the cytosol. So ultimately in this environment they have to interact with each other. The first one they may have interact with the 10th one. Suppose if the second one is a 16th, they may have interact with a eighth amino acid, which is a 16 by disulfide linkage, and all these things. So and what are the helical protein? If one amino acid interact with the fourth one, second, so they have a helical like structure. If they are not in that fashion, so they may have interacted like a far away amino acid by hydrogen bonds, so they may seat like structure. And they have not possibility, so they suppose one seat and second seat. So if two or three amino acid are not in that position to make interaction, so they may loop like structure. So such type of, but all these based on the how amino acid come into the cytosol and how they interact with each other. And ultimately in that fashion they have to make interaction, and they have a globular protein, or they have the protein folding. So that's the concept of protein folding. Yeah. What exactly protein folding? Usually some amino acid which are protein, as I told you, as the amino acid come into cytosol, so they have to make interaction. Okay. But usually the proteins are usually the amino acid which are hydrophobic in nature. So usually they are hydrophobic. Suppose first, if suppose have to five amino acids just come into the cytosol from the ribosome you during translation, and rest are also in the process. You just keep this in mind, and only five amino acid comes, and fourth one is a hydrophobic amino acid. So usually first, second, third are hydrophilic, and fourth is hydrophobic, and fifth, sixth, seventh are hydrophilic. Suppose only fourth are hydrophobic amino acid. So what will happen? These hydrophobic amino acid are not have a high propensity to be in the cytosol, because they are not water loving or the cytosol loving. So usually these proteins are going inside on the protein global structure. So what exactly? 1, 2, 3 protein comes and cover this fourth amino acid, and fourth, what, because these are hydrophilic, usually they prefer to be in the cytosol. So 1, 2, 3 amino acid come and cover this fourth amino acid, because that fourth is a hydrophobic, covered with the fourth amino acid, and fifth, sixth, seventh, which are also hydrophilic, also cover the fourth amino acid from the other region. So ultimately the portion which are hydrophobic, they are just go inside, buried inside on the protein, and ultimately they have a hydrophobic core inside of the protein. So that's the told information. What is the hydrophobic core? Hydrophobic core is means the region where it is highly hydrophobic. That is just an example. So okay, these are the region where the ligand or such type of things interaction, but that's just an example about the myoglobin. Now we just have to say different type of proteins and different type of interaction. Some protein have a, suppose this is a myoglobin only, this is a helical region. Some other proteins also have a helical and loop region. This is the carboxypeptide, they have a highly loop region also, and also helical region. And some seed region is like a purple in color, uh, helical region is like a blue in color. So these different type of proteins is found, different type of fold is found. So motif of super secondary structure. So this is defined as the secondary structure. Usually in the next slide I will describe in more detail, but is the regular secondary structure are connected by loop. What I say, suppose if 1, 2, 3, 4 amino acid, and 4, 1, 2, 3, 4, and 7, 8, 9, 10. If this, suppose if this amino acid and this amino acid make interaction with anyone, and 4, 5 amino acid are not in that position that have to interact with anyone. So these 4 amino acid are in the loop region, because they are not in that position that have to involve to interact, and these are, they may have interaction with each other. So there is a loop like structure. So loop are highly flexible because they are not in that any position that have to interact. So they have a highly move in this position or this position according to the environmental. And on this region, suppose if this is a beta sheet, and loop, and beta sheet, so they have a different type of motif, the super secondary structure, because that's not a secondary structure. Secondary structure is a different one, because secondary structure is alpha C, alpha helix, beta sheet, such type. But these are the super secondary structure. Usually we expect that this should be alpha helical region or beta seed, but okay, these are beta seed, these are beta seed, they interact, but these amino acids also have to interact with each other, but okay, it's okay. So ultimately these are like a super secondary structure. This is alpha hairpin, like the same thing. This is a blue one, as shown is a blue one is a, as I told you, blue one is a helical helix, suppose, and say, so they may interact with each other, they have some orientation, but some amino acids which are not in that position to interact with each other, so they have loop like structure and calcium binding. So alpha helix is some calcium binding protein, so calcium bind comes and bind with these loops to make it stable, so that's a calcium binding protein. And also DNA binding motifs also, because DNA comes in these motifs and they have to make interaction, so definitely they have some hydrophobic code as shown here. Beta hairpin, there's the same thing. Suppose if a seat is here and goes another one antipeller and there is a loop between, so okay, this is like a hairpin like structure. So this type of hairpin structure is a peller antipeller beta seat, and usually in the loop 4-5 amino acid, 4-5 interaction, 4-5 amino acid and 4-5 hydrogen bond, they have to interact with each other. Okay, so these are things of super secondary structure beta hairpin, as I told you. Beta meander is also, but suppose it's one seat and second is one loop here, then second with third in the second loop, third with fourth is third loop. So if such type of structure is found, is a beta meander. And Greek key is also, you have to just first and second, second with third, and third with fourth one, third with first one, sorry. If such type of things, and last interaction with the first one, so if such type of things is called Greek key. So these are the some type of motif which usually found in the protein. That's example. Beta alpha, okay, beta alpha is also a structure, same like things. Suppose beta alpha structure and GDP binding protein, they have some loop like structure. So ultimately that is super secondary. Beta alpha is also possible, alpha beta is also possible. So these are the things, just example, but ultimately you have to just keep this in mind, what is the thing behind that. They have some region where some other residue comes and bind with, and to make that them stable, like a hydrophobic core. So the GDP binding protein, some GDP come and bind with interact with the RAS protein is very important in the signaling pathway. So such type of things, just keep in this mind. And beta alpha beta is also found is right-handed or left-handed. What are the basis of the, what is the orientation? Because hydrophobic core, as I told you. So ultimately, if the beta and alpha and beta, so if they have to interaction with each other, and a beta alpha is a one loop and alpha beta is another loop, so definitely they have to interact in that fashion. So ultimately, they have some core, and okay, this core, they may interact with some other residue to make it stable. So the protein double is defined as the fundamental unit of the third three-dimensional structure able to fold by itself in the right direction. Okay, there is some typological error, but ultimately, what is the thing? Suppose if the light chain, heavy chain of the some what are the antibodies? Ultimately, they all, we just keep in this mind. What are the things? If they are different helix, so different motifs, so this motif also have a possibility to interact with each other or repel with each other, and ultimately they have in different orientation, and ultimately that orientation, one orientation is final one, which have a low binding energy, and that's the structure of the ultimate protein. Okay, the domain and classification, as I told you, what are the things? If all proteins are alpha helix, so these are alpha helical and loop region. The yellow region is shown in loop, and all the red region are helical region. So if protein is all alpha protein, it may possible like myoglobin. They also have a possibility to all beta, some helical region, but ultimately they have to say that okay, these are the beta seeds. Usually these proteins are also possible. So only beta seed, then loop, beta seed, then loop, beta seed, and loop, such type of things. And other is a, this one is a alpha plus beta, because alpha then beta then alpha then beta then alpha then beta then alpha then beta, such type of things, alpha plus beta. And alpha by beta means alpha then beta 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 something then alpha, that is alpha by beta. Or suppose beta alpha 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 then beta, so ultimately one is alpha then beta 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 then alpha, so such type of things is alpha by beta. Okay, that's a very important thing. I just, you just please keep this mind is very important, because that's a work about the nature work, and that's a very important for the circular dichroism concept. You just keep this mind. This is very important thing which I already told you. What are the alpha protein, what is the beta protein, and what is alpha plus beta, and what is the alpha by beta. These are really very important, and you have to just go through the some biophysics analysis. Then you have to be information that what is the alpha plus beta by circular dichroism and some other experiment. So these are some other region also, they have a possibility. Some multi-domain protein alpha beta fold consist two or more domain belonging to different classes. Some these are some things, some other terms, but ultimately you just keep this word. What is alpha, alpha plus beta, alpha by beta, beta, what are things that you just keep this mind. And I think we are just going too much away. Okay, up to now I just close up to here, and in the next one I think this would be fourth one, and you have to just get more information. What are the protein structure, how it fold, and what are the function, what are the structure function. Okay, in the next class I will describe in more detail. Up to now, thank you very much, and if you have any problem, any query, just text me, and it would be highly thankful to just subscribe my channels. Thank you very much.